Hey everyone, welcome back to Power Electronics. I'm Tim, and today we're talking about the flyback converter. So, I've included this in this Lecture 8 series because the flyback converter is indeed an isolated converter, but it's a little bit different. And to explain why it's a little bit different, we're going to have to look at the flyback transformer, kind of what it's named after, right? So, up until now, in these isolated converters, we've been thinking about the ideal transformer, let's say. And we know that there are some limitations, some non-idealities, leakage inductance, magnetizing inductance, which represents energy stored in the core. But really, what we wanted with these ideal transformers, is we wanted them to operate as close as possible to the ideal scenario. So when we actually make these things, we actually do want like a really high magnetic permeability in the core. We want as little leakage as possible. So people come up with like really fancy core designs to ensure that the majority of the flux actually goes into the core as opposed to going around. We want the coupling between the primary and secondary to be as strong as possible. And when current flows in to one winding, we expect it to flow out the other winding. But there's actually another option, right? And the other option, before I explain what it is we can actually abuse energy being stored in the core. Maybe abuse is the wrong word. We can utilize that fact, make it a feature instead of a bug. Right? And when we do this, when we try to store energy in the core, we design transformers a little bit differently. And the resulting transformer that we get is what we call a flyback transformer. So how do we do this? What does this actually look like? Well, what happens is that current doesn't flow in the primary and secondary at the same time. Instead, we put some energy into the core, one portion, and then we discharge that energy through another winding. That's the main idea. So what does this transformer actually look like? Well, it's largely the same. In a lot of ways, it's the same. So let's get a color going here. So we're gonna have a core, as before, except we're going to introduce an air gap into the core. Right, and this is kind of the same as before. We expect there to be some kind of there's going to be some length, right? Some average length through this core. And we can divide the length into kind of two lengths. So one length is the core material length, right? So maybe we'll call that L core. And then we're going to have another length, right? And maybe we'll use a slightly different color. The length of this air gap. And maybe we'll call this length L gap, LG. And for now, we're going to assume that the cross-sectional area of the gap and the cross-sectional area of the core is the same, even though that might not be the case. So we're going to have some cross-sectional area here, which we'll call A. Right, so basically the introduction of this air gap allows us to finely tune mu naught. Right? How? How does that work? Maybe I'll just say tune mu. Not mu naught, just the overall permeability mu. How does that work? Well, we have some relative permeability mu with the core, which we actually intend to be quite high. And there's also the vacuum permeability just of air, right? But for the air gap, because there's no material in this gap, the relative permeability must be 1. There's only the vacuum permeability, right? So over here, in this little space, we just have the vacuum permeability. So previously, when we were deriving the equations for the primary and secondary current in a normal transformer, what we found was something like N1, I1 minus N2, I2, and this minus sign is really just how you define the current, I'll just leave it in, is equal to the flux in the core, right? There's some flux flowing in this core if we have some windings, times L over mu A, right? And actually, what some people like to do is to define this as some kind of something similar to resistance, something we call reluctance. So they call this thing reluctance. And you can basically define a new system of equations, or you can define relations between flux and MMF and create kind of magnetic circuits. And we can do that here. And basically for different core materials, for a certain magnetomotive force, MMF, you produce a certain flux depending on the reluctance, right? It's something like V equals IR. So I'll just talk about that over here. So instead of V in magnetic circuits, instead of V equals IR, what we have now is something like Ni, or MMF, is equal to flux times reluctance. And reluctance has some, fancy R. I'll just draw it like this, because that's the best I can do. But in any case, this reluctance is actually related to the core material. And you can manipulate it in a very similar way to how you manipulate resistances. So series reluctances add, parallel reluctances, you have a parallel addition, basically. And thinking about this core in this way, in this reluctance model way, this magnetic circuit way, what we can do is actually find the new reluctance of this whole loop. So where we had before just L over mu A, what we have now is something a little bit different. So what we have now is one reluctance, which represents the reluctance for, say, the core material part, the LC part, and I'll call that reluctance for the core, is equal to LC over mu R mu naught A. And then we have some reluctance for the gap, RG is equal to LG over mu naught A. Right? And then you can come up with a very similar relation, right? So we can just add the two reluctances because they're in series. And factoring out the common A and mu naught, the total reluctance is going to be equal to 1 over mu naught A, and then we have LC over mu R plus LG over 1. right? And why is this interesting? Why do we care about this? Well, on the one hand, instead of trying to accurately tune mu r to adjust the permeability of this overall core, or you could say this reluctance of this overall core, what we can do is very finely tune some distance, which is a little bit easier. It turns out it's easier to test a core, see what its magnetic permeability might be, and then adjust the distance between two parts of the core to generate a specific air gap. You can tune the core a lot easier with this kind of method instead of trying to remanufacture a core to your exacting specifications, let's say. Another thing it does is that it significantly reduces the average mu naught. Or you could say significantly increases the reluctance. And as a result, increases the amount of energy you can store in this transformer. Right? So R is a lot smaller. Basically, you can it turns out decrease L. This, in effect, decreases the effective inductance, magnetizing inductance of the core, by decreasing the reluctance. So, I'll just summarize that actually. By decreasing the average mu, we increase the reluctance. It turns out that this decreases the magnetizing inductance. I'll just call it LM, the magnetizing LM, which allows us to store more energy in the core. It turns out we think of it as being stored in the air gap. The majority of the energy is stored in the air gap, you can say. And you might be wondering, we've decreased L. How could we possibly be storing more energy if the inductance is lower? Well, we store more energy if the inductance is lower because for a given voltage that we apply to this core, right, so if this is Lm, let's just say this is 1 to n, whatever, it doesn't really matter. But if we apply a specific V to Lm, think about the energy you can store in Lm, right? So the energy stored in Lm is equal to half Lm ILm squared, right? Well, we can think about the peak energy that we store in this is going to be related to basically the slope of the current as the current rises, right? So if you apply voltage for a certain amount of time, the current will increase, and there's some peak current that you can store, right? So we can say ILm peak is going to be equal to, let's just say it's starting at 0. It's going to be equal to V times some time, let's say T on, over Lm, right? Let's just say it starts at 0, right? So if we plug that in there, we see that the ripple is actually related. So V T on over Lm all squared if we simplify this, we're going to get half V T on, this is all squared, over L, over Lm, right? So basically what this is saying is if you reduce the inductance, then for a specific amount of volt seconds, you can store more energy, right? Because the current in that inductor will be higher, which means that this I squared will be higher. So even if Lm is lower, because there's a square in this I term, this is going to grow much faster, meaning more energy can be stored. So that is basically the whole idea. We decrease average mu, which increases the reluctance. As a result, this decreases the Lm, the magnetizing Lm, and we can control it very well by controlling this gap. We store energy in the core, right? But how do we actually use this? So we have a transformer, and I'll put it in quotes. It's actually a flyback transformer. And it's inherently different because we do store energy in the core, kind of the opposite of what we expected for a conventional transformer. How do we use it? Right? How is this useful? Right? Or how might we use it in a circuit? Well, I'm just going to show you what the flyback looks like, and you'll see how this energy storage mechanism works for the specific converter. There's an interesting derivation you can see in Fundamentals of Power Electronics by Ericsson and Maximovich, which derives the flyback from a buck boost. So it turns out that the flyback has a conversion ratio very similar to the buck boost, but for now, we're just going to look at the circuit and not analyze it yet. I'll save that for another lecture. We're going to actually spend some time on the flyback. But we'll just look at, how we store energy in it. So the flyback looks as follows. We have our input voltage, followed by our very special flyback transformer. This is connected to a MOSFET. This needs to be a controlled device, basically. And then we connect that to an output winding. Right, so this secondary side is our output. Which is then connected to an output capacitor. And then finally the load, right? So we have our load, we have C, this is our diode D, this is our MOSFET, I'll call it Q. And the dots are as follows. So we have one dot, the dots are on opposite sides. You could draw it either way, but this is how we'll choose to draw it. And then the turns ratio we'll say is 1 to n, although it could be n to 1 depending on what you want to do. So just to highlight exactly what's going on here, it doesn't look like we have an inductor here with this flyback transformer, but really the inductance is the magnetizing inductance. We're actually using the magnetizing inductance as the main energy transfer element, right? We're not only storing energy in this core, it is actually the only place that we're storing magnetic energy, right? Think back to the forward converter or the buck-derived half-bridge, full-bridge converters. All of those had output inductors, right? This does not. The flyback converter only has the flyback transformer, and that kind of is one of the main assets, right? So for the forward, you have to have a transformer and an inductor, for instance, or other isolated topologies. You have to have both a transformer and an inductor. Whereas for the flyback, we only need this one transformer. So we've kind of glued them together, right? That's kind of an asset. We've reduced the part count by 1, and one of the largest ones, let's say. So this is Lm, and you can kind of see how it should work considering there's only one controlled device. What we do is we turn Q on, and then when Q turns off, D turns on, basically. So in one cycle, or one part of the switching cycle, right? So for 0 to DTS, and from DTS to TS. So what do we have? We have the input voltage, our nice flyback transformer with the magnetizing inductance, which is currently being charged up. And then the secondary side is completely off, right? Really, the diode is not conducting, and we just have the output. And then in the second half, the primary side is disconnected, right? The Q is off. And then the diode does conduct. So this is what it looks like. And very briefly, I don't want to spend infinite time here. What happens is in the first switching cycle, what we're doing is we're charging up this magnetizing inductance, right? Current is flowing through this magnetizing inductance. We're applying a positive voltage across the magnetizing inductance, and the current is rising up. So we can imagine that the current is rising up and it's flowing through. The reason it doesn't flow through the secondary side, right, is because of the way the dots are pointed and the diode, right? So again, if current tries to flow into the dot, we usually say in the secondary side it flows out of the dot. So if it tries to flow out of the dot, well, the diode blocks it, right? So because these dots are on opposite sides, it reverse biases the diode, preventing it from conducting while the magnetizing inductance is charging up. Right, so here we're charging up Lm, and then over here we've established some current in the magnetizing inductance, right? We've closed or turned off the switch Q, meaning there's no path here. The only path that this current can flow is actually through this winding, right? The only loop that exists is through this winding, kind of similar to the forward converter, where when you turn off the switch, the magnetizing inductance forces another winding to start conducting. In this case, it forces the secondary side to start conducting. So again, we have current flowing out of the dot on the primary side, which means we expect the current to flow into the dot on the secondary side, right? So some scaled current flows into the dot on the secondary side and then flows to the output. So the magnetizing inductance forces the diode to turn on, right? Basically, the voltage changes such that the diode becomes forward biased. Right? And this is the fundamental difference, right? Normally, with a normal transformer, when we turn the switch on, we expect current to flow in the secondary side, and when we turn it off, we expect it to stop, basically. But here, we charge up the inductor in one half of the switching cycle, and then discharge it in the second half of the switching cycle. Right? That's basically how the basic idea of the flyback works. And then in the next lecture, we'll go into more depth about the specific operation and draw all the waveforms and figure it all out. And then after that, there's even more stuff involving snubbing and more non-idealities. But for now, that's it. Thanks a lot. I'll see you later.